Hi everyone, in today's YouTube video we will be finding the Thevenin and Norton equivalent of the following circuit. We have a voltage source connected with a resistor R1 that's connected to two resistors R2 and R3, and we want the Thevenin and Norton equivalent when connected to these two nodes. First of all, we know that V Thevenin is equal to the open circuit voltage and the I Norton is equal to the short circuit current going out. We're going to find our V Thevenin and R Norton by using mesh loop analysis, and we're going to apply KVL, Kirchhoff's current law, around each closed loop to find these values. We know that R Thevenin is equal to R Norton and that they equal the ratio of the open circuit voltage divided by the short circuit current. We're going to use mesh loop analysis. We're going to apply KVL around mesh loop 1 and mesh loop 2, and KVL tells us that the sum of the voltage drops equals the sum of the voltage rises around a closed loop.
So we apply this KVL into our first loop, and we have a voltage rise from the voltage source and a voltage drop from across R1 and a voltage drop across R2 of this current minus this current.
For our second mesh loop, we have a voltage drop across this resistor of this current minus this current, plus the voltage drop across R3 plus the voltage drop from an open circuit voltage, and there's no voltage rise. So now we have two equations by two unknowns, and we're after the open circuit voltage. We move I1 R1 to the right, R2, and we subtract I2 R2 plus R3. We know that since this is an open circuit, there's no current going out in this direction, so V open circuit is simply equal to I1 R2. And from our second loop equation, we want to find what I1 equals.
So we know that I1 R1 plus R2 is equal to I2 R2 plus the voltage from the source, and I1 simply equals Vs R1 plus R2 plus I2 R2 over R1 plus R2.
And since I2 is equal to 0, the open circuit is just R2 over R1 plus R2. This is an interesting result because we get that the circuit behaves like a voltage divider when it's an open circuit. And if you guys don't know what a voltage divider looks like, I'm gonna show you right now. This is something that you should keep locked away in your memory. You want to pull this up so you don't want to rederive it every time. V out, when we have a voltage divider, is just equal to the voltage source multiplied by this ratio of resistance. Now we're going to find the short circuit current. We're going to use mesh loop analysis again.
And we're going to notice that we get the same exact result.
And like last time, we're going to apply KVL, which tells us that sum of the voltage drops is simply equal to sum of the voltage rises around any closed loop. And for our first mesh equation, we're going to have a voltage rise from the voltage source, a voltage drop from R1 plus this current minus this current, I1 minus I2. Now we're going to have I2 minus I1 times R2 plus the voltage drop there. Since this is a short circuit, we're after the short circuit current, which is exactly I2. So we solve for I2. And I2 is equal to I1 R2 plus R3.
Now we're going to solve for I1 from the first equation, and like before, we get that it equals the voltage source over R1 plus R2 plus I2 R1 plus R2. We plug this result into our equation that we derive from the second loop.
And we get that I2 is equal to the voltage source R1 plus R2 plus I2 R2 R1 plus R2. So this ratio of resistance. We move I2 into one side, and we get 1 minus R2 squared over 2 plus R3 times R1 plus R2, which is equal to,
On the left side, we get the voltage source multiplied times R2 over R1 plus R2 times R2 plus R3.
and when we solve for I2, we get that I Norton, or I2, is equal to the voltage source. Now to find the Thevenin and Norton equivalent resistance, we take the ratio of the open circuit voltage over the short circuit current coming out, and we get that our Thevenin and our Norton
Are equal to R1 R2 plus R1 R3 plus R2 R3 over R1 plus R2.
The second way we can find the Thevenin resistance and Norton resistance is by finding the resistance looking in. We kill all the independent sources, and we apply a test voltage and a test current to find the resistance looking in. And by inspection, we find that this is a parallel resistance. That means R1 R2 over R1 plus R2. And when they're in parallel, we notice that they're in series with R3. And if we multiply it out, we actually get that same exact result.
R1 R2 plus R1 R3 plus R2 R3 over R1.
In a lot of cases, it's actually simpler to find the short circuit current, or I Norton, by simply finding the open circuit voltage and the Thevenin resistance and just taking that ratio. Because if you notice, it was a lot harder to find the short circuit current than it was to find the open circuit current. Excuse me, the open circuit voltage. I hope that was helpful. If you like videos like this, make sure to subscribe, like, and if you want a specific problem solved that's not too complicated, leave a comment.